Hi, this video is part of a series in which I learn about programming a retro video game on the Commodore 64 in assembly. The code I'm using is from the game Supernatural, written by Georg Rottensteiner. You may also know the game as Guns and Ghosts. This is not a tutorial, just me learning game programming. Enjoy the video. And we're on to the next step. And this step is it's so cool. This is the point where my gaming creation stopped. I mean, if I take this one more step, then I'll be further than I've ever been. We're doing falling, gravity, and jumping. And until now, the movement of our player sprite, which is basically just still the hitbox, has been kind of stale because we move 1 pixel per game loop iteration. And what if you want to, if you wanted to make that movement a little bit more lively, you're going to have to change that up a little bit, which is what we're going to do this time. And I've always thought that would be very difficult because I've looked at ways of implementing physics in video games and looking at artificial microgravity routines and all that kind of stuff. And it was so complex. And I suppose that if you really wanted to implement it in that way, you could, and you could make it very difficult. But this is so elegant, and I have to say that the code that we have is not, may not be very elegant, but the idea behind it is. And I've learned that the idea behind the code that we're looking at is really nice, and it's very important to have the right idea and then to go implement it. So, until now we had a sprite, basically we had a hitbox running around, and we could move it all over, but we're going to change things up. Before I really get stuck in, there's something that I wanted to say about the slowdown that I was getting in the WinVice emulator. I was using the regular one. But when you install Vice, there's a number of executables, and one of them is an accurate one. And I'm reading this off the SourceForge website. Is that as of version 2.3, there are 2 emulators. One is X64, which is fast, and the other one is the X64 SC, which is accurate. And the accurate one, called X64 SC, features a cycle-based and pixel-accurate VIC-2 emulation. This requires a much faster machine than the old one, emulator. The X64 emulator was there first, but the SC one is newer. I tried my code on a real Commodore, and it worked perfectly. There was no slowdown at all. And then I used the SC one. And the same effect was there. So there's no more slowdown, just using a newer version of the emulator. Yay, it worked. So that's good. Also, there's something I'd like to note after having uploaded the last part of this video series, is that sometimes code isn't present. Code that isn't, and I don't mention that, and that sounds a little bit weird, but some occurrences don't happen. For instance, when the player is moving left or right, there are points in the code where you might expect there to be a check of whether or not a value goes to 0, like an X position going to 0, or a Y position going across a certain value. But we don't do that because there are other ways of checking whether or not the player is trying to leave the field. Every level is surrounded by a bunch of characters, which is always there. So there's no way the player is ever going to reach that position where the x coordinate is going to be less than 0. So that means that when I don't mention it, it means the code isn't there, but it doesn't mean that nothing is in place to prevent things from going wrong. So that's kind of sort of an unmentioned kind of thing that is there. I'm going to try to talk about those things. Right. Why don't we have a look at what we're going to be building this time, because it works, and it's the effect is it's so funny. It's just like a real video game. As you can see, we have some new character designs. We'll have a look at that as well. But this is our player. Oh, sorry. I have to set up the joystick again. That one, and for some reason, save settings, save current settings. Yeah, done that. So here we go. This is our player, but watch what happens when I go off the edge here. Poof! I fall. But watch what happens when I push the joystick up. Poof! It just works. There's falling and there's jumping. So if I fall off here, woo! Jump, jump, and I can jump off the edge here. Boop, boop. Doesn't this just look like a... Doesn't this just look like a game? This edge is too high, so I cannot jump on here, but this is it. This is what we're going to build, and I can tell you that it is surprisingly simple. Let's look at the data again. I know there's some new things here. We have a jump table. Of course, we're going to use tables again. We have a jump table. We have a fall table. These are not the tables, but these are the sizes of those tables. And we're going to scroll down to the data section and look at the tables themselves. There's a player jump position, which is actually just an index into this table. So it might have been called player jump index. It's called position. And there's a jump table with a couple of values, and I'm gonna explain a little bit about how about what these values mean. And there's a fall index and a fall speed table. There's a player jump table and a fall speed table. I guess the player can only jump, or maybe other enemies are going to have their own jump tables. I don't know. The fall speed table is going to be the same for everything that falls. So now, what is the theory? The theory is, for one, that there is no longer a player down movement, right? We remove the detection of the player down, of the joystick down movement, because we are going to make sure that in every iteration of the game loop, the player is going to go down unless he is blocked, right? That is your gravity. And the up movement is going to be jump, so that's going to be different. We're going to be looking at the gravity first, because we have to realize that the player, if there's nothing under his feet, so if the collision detection routine that we analyzed last time doesn't block, we go down. Now, if we just let the player go down 1 pixel per game loop, it would look as stale as the other movements. But you've already seen now that's not the case. So how do we do that? We do that by allowing the player to move more than 1 pixel in one game loop. That means simply that we have to have a little loop within the game loop that says, don't move the player down just 1 pixel, but 2 pixels or 3 pixels. Well, that number is what you see here. Depending on the player's fall position, we record a number of iterations of that move the player down loop. So this moves the player down 1 pixel in one game loop, 1 pixel, and then the next game loop it goes 2 pixels, next game loop 2, next game loop 3, next game loop 3, and it goes on and on and on. You can sort of influence the fall speed, and of course the speed increases as you go. The player stops falling as soon as the move down routine blocks. That means the fall ends, and there is no real end to the to this. Now I'm gonna give away the secret. It's so elegant. It's so nice. The jump table is basically the same thing, but in the other direction. As soon as the player presses up, we record the fact that the player is jumping, and we let the player move 8 pixels up. That's an entire character, by the way, so that's no coincidence. Then in the next game loop, this is actually a good one. That's looking at these values. We're not moving the player up 7 pixels and then moving him up another 5 pixels. So that's interesting. Maybe, Okay, well, I'm going to have to look at this, because saying it like that, I mean, falling is okay, we can move him down 1 and move him down 2. This is obvious, but this is different. So it's not really the same. I'm kind of surprised by this. We have to really take a look at this now. So, but the principle is the same, that inside a game loop, I think this just sets the position. We move him up by 8. Let's just have a look. But the cool thing is, I was expecting the jump to be orchestrated completely. Like from the position where the player is, we jump up, and then we let him land down. I was thinking parabolas and all that kind of thing. But that's not the case. Jump just says up. It pushes the player up, and then the jump routine is finished. And what happens then? Maybe that's it. Anyway, what happens then is that the routine that pulls the player down, our artificial gravity, starts pulling on the player and starts moving him down again at fall speed. So you get a very interesting up and down movement that is half done by the jump routine and half done by the fall routine. So, and all the blocking, of course, is done by the routines that we've already written in the player control. So let's go to player control. Here we are. Player control, as you can see, is called once every game loop, right? The game loop still hasn't changed a thing. So we load the player jump index. Maybe it is position. I've called it index, but maybe I'm wrong. But we're going to look at the down movement first anyway. So let's assume that the player wasn't jumping, so the position is 0. This says if it's not 0, then the player is jumping. Obviously, we are not. And then here's the old code. The old code said, well, is the player moving the joystick down? And if so, then we do player move down. Now, we just do player move down, always. And the result of player move down is either 1, we load the accumulator with 1 or 0, depending on whether it is or isn't moving down. So if it equals 0, then we were not falling. And not falling is this routine, and it says, the player fall position, the player fall index goes to 0, store that, and then we just continue with the rest, which was not down pressed. So we're done with all the down stuff. Now, the interesting case, of course, is what happens if we were falling. Yes, we've moved the player down 1 pixel, player fell. What happens at player fell. Well, we go to that declaration. There we are, which is basically just a little further down in the code. The player fell. We load the current position. We check the value in the fall speed table. If that equals 0, then the fall is complete. When the fall is complete, we say, okay, loader fall position, compare it to the table size. If we're there, then the fall speed is at max, and we just continue with the rest. Otherwise, we increase the player fall position, and we pick that up on the next iteration of the game loop. Now, if we go back to this case and we load the fall speed value, and it's not 0, it's something else, we store that in parameter 5, we decrease it. If it's come to 0, then fall is complete. If not, move the player down, check for blocking, by the way, and jump back to fall loop. So this is the loop inside the game loop that says, okay, take the value from the table and decrease, move the player down as many times as it says there. So that's 1 pixel, 2 pixel, 3 pixels, whatever number of pixels there. This may mean that the player is blocked at some point. So I wonder what happens if we try to move the player down, but we're blocked immediately. It tries to keep on doing that a couple of times, so that may mean that we're motionless, or can we control? I think we can still control the player while we are moving, so while we are falling. So we jump to the fall loop, and when we're done, the fall is complete, and we just go back to this and everything, so that everything goes as planned. So that is it, basically. That is it for falling. We just have a little table, and we make sure that we iterate the number of times that it says in that table, and we move the player down. Of course, the player down function here is quite elaborate and allows us to check whether or not we are hitting stuff. There's one thing that I forgot to show, and we can do that now. We've done the falling. That is the falling. So we're doing this at every game loop. Let's have a look at the character set editor. And I'm going to have to load from file, character set project. We have some characters. This is the background character. We're filling the background with this. These I don't know. This is our character set. These are our letters. Very well designed by Trevor, I think. And then this at character position 96. Excuse me. Character 96. We have some. This is the ground stuff. This is the stuff that we walk on. And this stuff from 128 is our border stuff. It looks like brick, rock, basically. This looks like ground. Now, as you can remember, maybe, is that the routine that checked for blocking actually checked characters that were larger or equal to 128. But that routine has changed. It's gone to 96. So any character that is defined from this point blocks. But it's nice to see. This is, Trevor, he understands 8-bit design. These are multicolor characters, so you have to realize that this is all... Can I show the grid? Show the grid. In multicolor, this is your grid, which is extremely coarse. See, these are 2 pixels, 2 pixels, 2 pixels. And still he manages to design something that really looks, it looks good. And it connects, you can put these together and they just connect. and they make something that looks like ground. Very well done. Okay, done that. Let's look at what happens to the jumping. Okay, same thing. As we come into our player control, from the last game loop iteration, these values, these jump position values, of course, tell us what we were doing in the last iteration. So we sort of have, a transfer of information. We just have a memory position somewhere that says, hey, we were in the jump table. So let's just say we were not doing anything the last time. The player is jumping. Okay, so nothing is happening yet. But what if not left pressed, not right pressed? I have to check where we did that. Not down pressed. Not up pressed. Okay. Not down pressed, and then we were checking for up. Right? So player is jumping function is the same as this one. Player is jumping. So either we check by checking the joystick. If we pressed up, hey, player is jumping. Or we were already jumping. It says, hey, we were jumping, and we go to player is jumping. So what happens at player is jumping? Player is jumping. We increase the jump position. That is funny because I don't know what it was when we started. How is it initialized? Player jump position. Let's look at where this where this is used, because if we weren't doing anything yet, we increase it there, we load it. Right, that's funny but we weren't there yet. Jump on, haven't been there yet. Jump blocked. Oh, it's initialized with 0. See, this actually initializes it with 0. So player control, we go back there. Sorry for all the jumping around in the code, but player is jumping. Let's go to the declaration. And the first, if nothing's happened before, then we increase the position. So the first, if it was 0 and we increase it, we're skipping the first value, basically, because it's 0, and then it goes to 1, which was, that value was 7. And anyway, we increase it, we load it, we compare it to the table. If it's not the table size yet, then we jump on. Otherwise, if it is the table size, we set it back to 0 and the jump is complete. Jump complete, I think it just goes into normal operation again. Jump complete. So what if we are in the middle of the table, we load the jump position index, we get the value at that point, which is 7. If it's 0, I think the values at the end were 0, right? If it's 0, then the jump is complete. So that's at the end. Was it 0? Let's 269. Remember that line number. Jump table. Right. At the end there are zeros. Right? Zeros. 269. Go back. Right. So where were we? We have the jump position as the index. We load the value. If it's 0, jump complete. If not, we store it in parameter 5. We move up. If that returns 0, then the jump is blocked. So if we bump our head into something, and basically if we bump the lower character of our hitbox into something, We decrease parameter 5. If it's not, then we go to jump. It does. It moves the player up by 7 pixels. That's funny. I don't really see how that works. Jump blocked, okay. If jump is blocked, then we put it back to 0, and jump stopped. Jump stopped is probably just right. It's just there. So how does this work? I would say that if my first conclusion is that since the first thing we start doing, where are we? Not falling, not down pressed. Player is jumping. The first thing, if it starts at 0, and the first thing is we increase it, we go to 1. So we skip the first value. I think that is unintended. So that, I mean, you can call it a bug, but it just the first value is ignored in that table actually. We check if we're at the end, which is all logical. If we're not at the end, then we jump on and we load the value that is there. We load the. Oh, okay. Yes, well, it was 0. It is now 1. We get that. We use the 1 as the index into the table. We get the value 7, because that's the value at that point. If it equals 0, no, it doesn't equal 0. So we store that in parameter 5. We move the player up. And we decrease parameter 5 until it's 0. So we move the player up by 7 pixels. Then in the next iteration of the game loop, jump complete. I think what happens. That doesn't happen, does it? No, because we do. The next time we say, hey, player is jumping, because, we're at position 1 in the jump table. Player is jumping. We increase the table again. How large is that jump? Let's look at the jump again. How high is it? Actually, it is quite high. If I go here. Oh, look, it's easily. Oh, look at how high the jump is. So it does. I thought it was silly to think that it would, but look at how high it jumps. That's at least 2 characters. So that's at least 16 pixels that we're jumping. So it's not that strange actually. And during the jump we can move, by the way. I noticed that. Okay, so it does work the way I thought it worked. It's just the jump is much bigger than I thought. So in the first loop, we move it up. The intention is, if I go down to the jump table, you see, if the index is 0, this is what we mean to do. But the first step it takes is to increase the jump position, so it goes to there. What would actually be better, and I don't know if it's going to crash now, but since the first thing we do is to increase it, gonna do that. No, the effect is the same actually. Okay. Probably perhaps I'm missing something, but on the first iteration, let's just go down to the data again because I want to look at that table. On the first iteration, we move the player up. We never do this, so we move the player up by 7 pixels, then by 5, then by 3, then by 2, then by 1. So that's 7 and 5 is 12. That's 15, 17, 18, 19. So that's actually 20 pixels, something like that. We move him up 20 pixels, and then the jump ends. Let's look at that routine once again. Player is jumping. Let's player is jumping. There we go. We increase the jump position. It was 0, so it goes to 1. We load it to check what it is. Is it the table size? If it's the table size, then we're done. We return it back to 0, and the next time we come in here, the first thing we do is to increase it. So actually, I should do that. And that, it should really, I think it should increase our jump even further. Our jump distance even further. See that? Something's happened. It makes a very weird extra jump, really. It doesn't. It looks as if the 8. I think I might be able to jump back on this thing now. Yeah, see that? It appears to be doing 2 jumps actually, like an automatic double jump, but it sort of lifts us up to the to-do. It's funny. It's actually enjoyable already. I'm not even scoring points yet, but it's I'm feeling that it's a game. So this is weird. And perhaps I haven't really fathomed the depths of the oh god, I lost my way. Player is jumping. Put it back to 0. So we increase that thing. We load it, check it to the table size. If it's not equal, then we jump on. The jump continues. We load it into the position into X. We get the value, and we just move the player up by that amount of pixels that we find there. Let's see. Jump continue. Jump complete. Jump complete. Okay. Table size. Otherwise, jump complete. By the way, if we jump complete goes here, and then we check for left and right. So this makes that we can still move. The same is for player move down. Player fell, so blah, 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 not falling. Player fell. I'm pretty sure the player fell. Player is jumping. Fall complete. Fall complete just takes us back to fall complete, right. Comes into here as well. So that means that when we fall, we can go left and right as well. So. And that is an important game mechanic. Don't forget, if to be able to move left and right inside of a jump is very important. We can all remember the games that says jump, and it finishes like a complete jump. I played Chucky Egg. I'd never played Chucky Egg until like 2 days ago, and I played it, and that's one of those games that lets you jump, and it goes and makes the funny noise. It's like an entire orchestrated jump. But the trick is to not do that. Just push the player up and then let gravity take over. It's perfect. So that is it for falling. Just the one question: why does that that first value get skipped? I'm gonna look into that, and I'm pretty sure when I think about it, I'll know by tomorrow later today, and I'll come back to it in the next video. So thank you for watching again. I hope you've enjoyed it. Questions, yeah, go ahead. Remember, this code is available on my GitHub page. I'll put a link to my. If you go to my web page, thehighlander.nl, you'll find links to my GitHub page and this project, so you can download the code. You can get the IDE, and you get Vice and start doing this yourself. And if you just want to watch, you're welcome, of course. Well, thanks for watching, and I will see you next time.